Okay, welcome Anna and Erez and Michael, and hopefully we'll get a couple more coming. We'll see. Hopefully the quiz went okay. Are there any questions that any of you have before I get started in the quiz? Any questions? Okay, if there's no questions, I think I'm going to jump into the quiz. And let's take a look. Okay, a survey was done to see if there's a relationship between political affiliation and first COVID-19 symptom for those who test positive. The results of the survey are shown below. I want to let you know that this is a lie. Why is it a lie? Anyone know? Okay. Yeah, the data. I don't know. I don't think a survey was really done, but you could imagine a survey being done on this. Okay, and there may be a relationship between symptoms and political affiliation. If you were to guess, do you think there's a relationship? I would say probably not. And so you shouldn't be too surprised at the p-value, by the way, when we get there. Okay. So what was the name of the test you will use? State the null alternative hypothesis, write down the test statistic and p-value, state your conclusion, okay, in the context of the study. By the way, context of the study is important. So words that you have to have if you're doing context of the study are things like political affiliation. Okay, those words need to be there. And symptom. So that is real important. If I ask you context of the study, that means you have to have words about what the study was about. Okay, and that's really important, because if you don't, I take off points. So I'm actually going to copy and paste it in here. Just easier that way. Okay, so what test do you think we're going to be using to find out if there's an association between political affiliation and what's the name of the test? Yeah, this is a test for independence. And if you want to write chi-squared, you can. You probably can't see it's too low, is my guess. Chi-squared test for independence. Any questions on part A? Okay, this is definitely two qualitative variables. The first variable is going to be what's your political affiliation, and you might say Democrat. And that's a word, not a number. It's not yes or no. And the second question might be, what was your symptom? And you might say, oh, I was coughing. Okay, and that's a word. You wouldn't say 7. So that's really important to note that when we're talking about a chi-squared test for independence, that means we have 2 survey questions, and both of the survey questions are qualitative, and we're not comparing one group with another. We're seeing if there's a relationship, an association, or if they're independent. A lot of ways of saying the same thing. Any questions on that? Okay, now state the null and alternative hypothesis. What word must be in the null hypothesis? What word must be in the null hypothesis anytime you do this test? Yeah, part of it. Independent. Independent. So that's just something to note, is that for the null hypothesis, we're going to say that political affiliation and symptom are independent. Any questions on H naught? H1. Okay, what word must be in H1? Yeah, dep. I'll take dep. Dependent. Okay, so I like to copy and paste. Makes life a lot easier. And then just adjust what I need to. Political and affiliation and symptom are dependent. Will it take off points if we add the probably because this is not about distribution. This is definitely not about distribution. This is about the answer to what is your political affiliation? So distribution, but I won't destroy you, at worst 1 point. Does that make sense? So you don't have to be so upset. So it's not like I'm going to kill you. And I want to remind you that losing points on the quiz is sometimes a good thing. Let me tell you why it's a good thing. Because my guess is that if I take off a point because you didn't say the word distribution, and because you said the word distribution, and then on the final exam, I give you a test for independence question, you'll remember not to say the word distribution. And don't forget that most of the points in this course are the 2 projects, the 2 write exams, and the final exam. This little quiz is like almost meaningless in terms of your grade. So you don't have to freak out. Just remember not to make the mistake on the final. Does that make sense? So I like to say the quizzes are for you, the final is for me. So the quizzes is for you to remember what you need to remember to do, and the final is for me to decide what grade to give you. Does that make sense? So that's how you should be taking this. So try to remember not to use distributions because it's not about distribution for test for independence. Okay, so there's H naught and there's H1. All right, so now that we have those, we now need to write down the test statistic and the p-value. Well, to do that, we need to go to our calculator. And now we're towards the bottom, by the way. So what number? No, not a lot left in this class, by the way. So what number for this one? It's not 22. 21. Remember, this is A, and this is why you got to get part A right. Part A is really important. Part A is chi-squared test for independence. And if you know that, then you should know this is a test for independence. It's not a trick question. Okay, once you know part A, it should be really easy to know which one to click. One of the reasons why I asked you to do it. You just looked wrong. Okay, as long as you got it right on the quiz, that's what matters. And more important was the final. So we're doing the chi-squared test for independence. Okay. And enter the observed values and hit calculate in the chi-squared test statistic. And the p-value will be calculated for you. Leave blank the last rows and columns that don't have data values. Okay, notice just because this is kind of messy with the quiz, I didn't even know this one did this one also. So in this case, you put all the first ones in, and the first were 98, 55, and 70. And it doesn't matter whether you do rows and columns, you'll get the same answer. So 98, 55, 70. And then the seconds, let me double check, were, oh, sorry, those were the seconds. It actually doesn't matter which one you do first, but let's do it right. 89, 42, 76. And I like to use the tab button because it kind of gets you to the next thing. And then for the seconds, that was the 98, 55, 70. And for thirds, it was 49, 40, 45. And then we're supposed to leave everything else blank. But I do need to scroll down. It goes up to tenths if you want. And hit calculate. And our test statistic is chi-squared. Maybe I'll keep 4 decimals. It's prettier. And that's chi-squared. And then the other one's the p-value. And that was about 0.2695. Any questions at all on finding the test statistic and the p-value? I'm hoping that you're at the point where you've got this down. Yeah, if you do it by columns, you get the same number. Okay, something I mentioned, what I'm not going to do, and you probably don't want me to do, is to prove that mathematically. But that could be proven that you get the same number. And it makes sense, is that if political affiliation and symptoms are independent, well, then symptoms and political affiliation are independent, right? Because if you switch the rows and columns, that means you're switching those two words. And that says the same thing, doesn't it? Yeah, so that's not a mathematical proof, but at least it sounds good, doesn't it? Okay, that they should be the same. So the nice thing is you don't have to worry about it. You don't have to worry about which are rows and which are your columns. Okay, now we're ready to state our conclusion. What are the first words for our conclusion? You're supposed to be used to this. We did a hypothesis. Yeah, there is. And then what are the next two words? The next one should be automatic, and the third one, the fourth one, you have to think a little bit. Statistically. And now we look at our p-value. And the p-value is about 0.2695. And that's bigger than any alpha you'd use. So that means it's insignificant. Evidence to conclude. And now we got to write it in the context of the question, which means, as I mentioned, you have to have the words political affiliation, and you should have symptoms in your sentence. So to conclude that political affiliation and COVID-19 symptoms are, you could, when it's insignificant, you could either say dependent or independent. I like to say dependent. And that will work whether it's insignificant or significant. Dependent always works. On the other hand, if you find significant evidence, you have to say dependent. In this case, it's insignificant, so it's fine. So, are there any questions about any of these parts? Okay, you'll notice, by the way, that it's the same question as you had on Thursday. Not the first paragraph, but the A, B, C, and D. Okay, and I can tell you it's exactly the same question, letter for letter. How do I know that? Any thoughts? I made it, but even more so, I copied and pasted. Yeah, I just took last week's quiz and I hit copy and I hit paste. Okay, and I changed the first paragraph. And that way you're getting used to the way hypothesis tests, I word hypothesis test questions. So that when you get to the final, you'll understand how to handle a hypothesis test. Any questions at all on question 1? And by the way, question 2, I copied and pasted. A, B, C, and D. It's exactly the same A, B, C, and D. Okay. The hard part is to know which test to use. Okay. And the hope the rest wouldn't be. What if you got the words to conclude? That one's okay, actually. That's not so important. Because if you got the words to conclude, you're not referring to some other test. But distribution refers to goodness of fit or homogeneity. So that's why it's a problem if you write distributions. But conclude is in all of them. So that one I'll let you go with. But the distribution means you might be confused about which test you're using. Does that make sense? There's a reason, you know, I'm not just like mean sometimes and nice other times. I try to test you on, are you getting the point of the test, of the statistical test? Okay, so next is, do men and women differ when it comes to the type of car they drive? The table below shows the results of a survey. Okay, and again, I always like to warn you, especially since it gets put on YouTube, is that I just totally made up these numbers. I did not do a survey. I did not look up a survey, but I can imagine a survey being done. Could you? So that's just a big note. But I did hit record, right? Maybe I should double check. Let me double check. Usually I like to double check. I think I did. Yeah, I'm recording. Okay, so here we got a survey. And now, what's the name of the test you're going to use? So let me copy and paste so that we can pop it right into the answer. You don't have to do the copy and paste, but I think it makes life a lot easier to have it right in there so you can type right where the question is. What's the test? Yeah, this is the test for homogeneity. You don't have to write word chi-squared, but I like to. So this is a chi-squared test for homogeneity. When I read published articles, I usually see the word chi-squared test there. So I try to model what I see in the real world. Okay, and by the way, we know it's chi-squared test. Here, we're not looking to see if there's a association between the two or if they're independent. We want to see if there's a difference between the way men act and the way women act. And that's about distributions. So the distribution of answers for men and women or driving for men and women the same or not? Okay. And by the way, just a footnote, I was asked a survey question. No, I wanted to see if someone else would know the survey question this morning at 7 in the morning. I got an email. It was a fishy looking email from our president of our college. So I asked the president, you need to tell me the last time I came to the college, what was my vehicle? And I figured if the person didn't know, it was a fishing. You think it was a fishing? Last time I came to teach, yeah, it was a fish actually. So be real careful about these emails. They wanted me to, you know, buy $800 of stuff for them. Like, that sounds fishy. The president of the college wouldn't ask me to do that. Anyone know last time I came to teach at the college what my vehicle was?
Let me translate that. Is anyone a stalker in the class?
At this point, it's too late. I'm not giving any money. No, not right. Good try. Skis. last time I went to the college to teach, I skied to get there. So I figured anyone fishing is not going to say skis. So it just kind of randomly came at the same time that I'm doing this. Okay, so I'd be a weird person, not sedan, truck, or SUV. So the name is homogeneity. State the null and alternative hypotheses. So again, H naught. And unlike the first question, what word must be there? Yeah, distributions is even better because we're talking about two different. So what we can say is the distributions of vehicle differ by gender. And there's lots of ways of saying the same thing, but the word distributions needs to be there. You could say the distribution of vehicles is different for men and women. That's fine too. There's lots of ways of saying it. Any questions on H naught? Wait a minute, sorry. Do not differ is what I meant. Yeah, if you say distribution, I'll let that happen. I like distributions because then it reminds you that there's two things going on. So H1 is what I said before about H naught, is the distributions of vehicles differ by gender. Any questions on that? Because remember, H naught is always the equal one, right? And equal means they don't differ. H1 is the not equal to, and that means they differ. That's one way to try to remember it, because it kind of goes on to what we did before. Any questions? Okay, so now we've got that one. Now we need to do test statistic and p-value. So again, we have 104, 72, 48, 95, 126. So I need to go to my calculator. Oh, shoot. Let's try this again. And which calculator do I use now? And the key is, if you saw the name of the test, it should be very obvious if you got the name of the test right. Yeah, now it's 22, test for homogeneity, because that's the test. Okay, so what I'm going to do now is we have our 104, and then tab, and then 295, and then tab, and then 72, tab, 126, tab 48, and tab, and 201. Any questions on that? Okay, let's scroll down a bit. Hit calculate. And there's our test statistic, 16 point, I don't know. How about 607? Then I don't have to worry about rounding. So chi-squared is equal to 16.607, and the p-value is equal to, we'll get there. Just take a bunch of decimals. About 0.000246. Okay, do you need to be given the level of significance, by the way? Are you asking, was it supposed to be A and B columns on the calculator? So the calculator, the way the calculator works, that's why I just use tab, because then I can remember, is the first is A, the second is B, basically. Then the first is A, the second is B, first is A, second is B. You'll get the same answer. Yeah, so it's just kind of the way it is. And that has to do with the fact that the screen gets small on the quiz. There was no good way of fixing that. I'll try again, but as good as I can get. Okay, so now that we have our p-value, 0.000247, and I didn't give you a level of significance, and you shouldn't need one. And how come? Yeah, p-value is, I like the word minuscule better than small. Okay, this is tiny, tiny. Okay, smaller than any level of significance you'd ever care about, especially for something that doesn't matter that much. Okay, so what you'd say is there is statistically, and I'm going to write strong, because when you have a very small p-value, you can say the word strong. Statistically significant. Because our p-value is small, so we have significant evidence to conclude that, I think the easiest thing to do at this point, copy and paste H1 and then uncapitalize the T. That the distributions of vehicles differ by gender. I try to make it, by the way, reasonable. And I don't think symptoms of coronavirus have anything to do with political affiliation. Maybe I'm wrong, but it doesn't feel like it. But I'll tell you, if you're looking at trucks, are there women that have trucks? Yeah, but a lot more men do. Okay, I actually have a good friend who's a woman who has a truck. But I have a lot of friends that are men that have a truck, and I don't know that many women. So I thought that would be, not surprising to see a small p-value. Try to not to be surprising, by the way. I try not to give any trick questions. So you should worry if your p-value doesn't fit what you think it ought to fit. Okay, any questions at all on this quiz? Anything surprising about it? No, women drive fewer trucks, typically. But what this says is not, this does not tell you who drives more. This tells you there's a difference. Yeah, no, women are less likely to drive trucks, at least in my friends. I have a lot more male friends that have a truck than female friends, and neighbors too. Doesn't mean it's always true, but just what I've noticed. And so I'd be very surprised if it was different than what I've noticed. Okay, but again, you didn't have to know that. You got a p-value, and that's it. Okay, yeah, this does not tell you who drives more or who drives less. It does not tell you how they're distributed differently. It just tells you there's a difference. So in particular, if you were doing some kind of survey about what kind of vehicle do you have, and you want to do a very large study, then you want to stratify by gender. Because if you got such a small p-value, then if you don't stratify by gender, you may end up with bias. Okay. On the other hand, if you wanted to study the COVID, okay, by the way, I made these numbers up, but if these numbers were all correct, and if you wanted to study the COVID, and you wanted to look at symptoms, do you think you would need to stratify by political affiliation if you were doing a statistical study? Okay, well, what was our p-value? P-value was high And we didn't find out there was any relationship, which means you don't need to worry about political affiliation if you're going to be doing a study on COVID symptoms. Does that make sense? So that's kind of the point of all this. So you're saying, but there are more women who drive a truck. Well, that's true. 126 is bigger than 72. What's wrong with just saying that, though? What's wrong with just comparing those two numbers, saying, women are more likely to drive a truck? What's the issue? There's a big issue. Yeah, more women were surveyed, right? Notice that there were like over 600 women surveyed, and there are only like a couple hundred men surveyed. So of course, there's going to be more women in all of them, but it doesn't mean they're more likely. Do you see the difference? Yeah, proportional. And again, what we're not doing is I'm not doing the mathematics behind it. But in the mathematics behind it, it has all that proportionality stuff. If you want to learn all the mathematics, you need to change a major and be a math major. And then you'll learn all the mathematics. I had to. But you should notice that, the sample size is much bigger for women. And that happens. That's fine, not a problem. Any questions? Okay, if there's no questions, I think I'm going to move on to talk about the big next topic. Today is actually, my plan is we're not going to do any hypothesis testing. It's been a while, hasn't it? It's been a long while since we haven't done hypothesis testing. That one, there we go. Okay, but Thursday we're going to do hypothesis testing. So there is hypothesis testing in chapter 12, but I'm waiting on it. There's a whole lot more that's really important to talk about besides hypothesis testing. So in particular, we're talking about regression analysis. And you've probably heard about things, the word correlation. I'm sure you've all heard that word. Anyone not hear of it? Things being correlated before? Okay. Okay, you've probably all heard it. It comes up all the time. What you don't know is the deep mathematics behind it. And at the end of this week, are you going to know the deep mathematics behind it? No. No. You can know a little bit of mathematics behind it. Deep mathematics is brutal. It's brutal. I went over it a couple weeks ago in my third quarter calculus class, by the way. I don't think they were very happy about it. Actually, about a month ago. And they didn't even understand it. So just let you know, there's a lot of math behind everything we do that we just kind of let the calculator do for us. And that's how it's going to be today. That's a big note. So just a note in terms of this chapter and what this whole correlation is about is I want to talk about what it is that the kind of situation you must be in to be able to do correlation. So I'm going to call that regression analysis. And that is, you have to have two variables. Kind of like when we had chapter 10 and we had two variables and we had to do a hypothesis test for the difference between them. But this is different. So if two variables are looked at and you want to see if there is a linear relationship. And we call that a correlation between them. Okay, the variables must be quantitative. Okay, so for example, the political affiliation and symptom, that does not work because those are not numbers. The answer to what is your political affiliation is not a number. So you can't do this whole regression analysis stuff. Google Smart, it knows I need a VA. Okay, so that is important. They do not need to be the same units. So when we were doing the hypothesis test for a difference between two means, we had to have the same units. It didn't make any sense to do a hypothesis test for the difference between inches of height you are and weight, because you can't subtract, 5'7" minus 250 pounds. It makes no sense. On the other hand, if you're doing regression analysis, it does make sense to look at height and weight and to see, is there a correlation between height and weight? As you look at someone who's taller, do they tend to be heavier? Does that make sense? And what do you think? Do taller people tend to weigh more? Yeah. Does that mean that if you're taller, then you weigh more? So does it mean that if you're taller, then you weigh more? So people who are taller are always heavier than people who are shorter. Does that mean that? No, it doesn't mean that. But if someone is taller, they're more likely to be heavier. Do you see how that is? So I want to mention that when we're talking about regression analysis, it's not an absolute. We're not going to be able to say that this, if you know this, then this must be true. That you can't do. But what you can do is say, if you know this, then we have a better guess at this other thing. Any questions on that? Okay. So, and there's lots and lots and lots and lots of examples of linear regression and regression analysis. And I want to talk about the most important example of all examples for where we live. What is the most important thing in the last 40 years or so people have collected data for, that people care where we live, not where anyone else lives, but where we live? See if you know. Talking about Tahoe, that's where I live. Okay, this is officially not an online class. I'm assuming you all live in Tahoe. It may not be true, but we're all supposed to be living in Tahoe for this class. Whereas next I'm teaching an official online class, even though there's all basic classes are online, and they could live anywhere. Global warming is really important everywhere else too, right? If you live in India, everyone cares about global warming. Snowfall is important, but it's also important in, say, Colorado. All right, let me scroll and you'll say, of course. Any idea what this is? Yeah, Lake Clarity. Do you agree that's the #1 data collection that people care about in our town that they don't care about anywhere else? Nobody cares about Lake Clarity in Sacramento. Okay, but our town, we're all about Lake Clarity. So what I did is I want to give you a historical. And the cool thing is this was presented to the President of the United States at the time, this graph. And you can see the years. Anyone know who it was? Based on the year that it ends at? This is history, not math. Yeah, that was Clinton. So this was presented to Clinton. And the cool thing is, my statistics student was there when it was presented to him. That's cool. Okay. Now, what she was doing was serving him lunch. He was eating in a restaurant in the hotel, and she was one of the servers. But it's still cool. And she told me about it, and she told me about this too. So they showed this to him, and we have two quantitative variables. And the two quantitative variables are year, which is the x-axis, and that's definitely a quantitative variable. If I asked you what year is it, you would give me a number, right? To 2010. Sorry, 2020 is what I meant. Okay. And meters. So if you don't know how this works, it's kind of cool. I've talked to them in depth about it. And they have a nice picture. They have a boat. UC Davis, I don't know if you know, is in charge of doing testing for lake clarity. And what they do is they take a seki dish, and a seki dish, all it is a white plate. And they tie it up, they tie it to a string, and they let it go down until they can't see it anymore. And then they measure how long that string was when it hit that point at which they couldn't see it. Any questions on that? And notice when you do that, you measure how long the string was, and that's a number. Okay, and this is in meters. Hopefully you can handle meters. And they probably do it in meters because they're scientists. Scientists like meters, which makes sense if you understand. Okay, and this is the data they got. Now I want to mention something that was a really cool conversation I had with them. I talked to them about this, and I talked to them about how they're doing it. And they gave me some details. And I said, well, when do you measure to get that value, like say in 1992, which might be that value over here? And do you know what they told me? They told me they don't do one measurement. They do a lot of measurements. And I want to let you know they made me smile. How many measurements do you think they told me they did? The hint is they made me smile. I'm looking for a number. Should I tell you? 31. Okay, they said 31. It's like they took my class. I was pretty excited. So they told me they did 31 measurements, and then they took the average of the 31 measurements. And if you take the average of the 31 measurements, then it's normally distributed. Do you see how that works? So to do regression analysis right, it turns out you do need to have a normal distribution. And the best way to do normal distribution is what's called subsampling, is what they did. Means that they do a sample of 31, take the average, and use that as your data value. Okay, any questions on that? And if you do that, then everything in regression analysis basically works. They had to do some other things. They couldn't do it on very sunny days. Anyone know why? Yeah, reflection, and then you can't really see when it goes down. So they had to wait until either it was windy enough so that the waves kept the reflection from happening, or there were clouds above. So just some notes about how they do this. Okay, so now you look at this and you say, does it look like there's a relationship between year and meters? Does it look like there's a relationship? Or does it look like it's just random? Yeah, it looks like a relationship. Are you ready for a trick question? Okay, so what you do next is you say, well, we have this relationship. It looks like we have a relationship. I'm going to actually draw. And you can just, I'm going to eyeball it. That's not how we're going to do it later. And you can draw a linear relationship. They did a little more advanced. I'm not going to do the advanced stuff. But you can draw a linear relationship. All right, ready for the trick question? Okay, when you have a line, okay, let me start with not a trick question. Who remembers the regular standard equation of a line? Y equals what's the standard? Mx plus b. Okay, so a couple things to note. Be careful of this. It's better not to use y equals mx plus b because that's not what statisticians use. Sorry about this. Don't blame me. Y equals a plus bx. And there's a reason for it, and I can't explain it. Sorry. If you take my third quarter calculus class, we're going to be doing that actually tomorrow morning. And talk about how this works. But that's not going to happen to any of you. So at this point, trust me. Okay. So we have, and in terms of that, we have two numbers. We have a slope and a y-intercept. Is the slope of this line positive, negative, or zero? Okay, now what you didn't remember is what I told you. This was a trick question. It's negative. Total trick question. I've never given it a test, by the way. So it's a total trick question. Take a look real carefully at the y-axis. Look at the numbers. Do you see? 40, 35, 30, 25, 25, 15. So that's just a note. I wouldn't do that to you on a test. But I like to give you real life, especially this is like our real life, the most important thing that ever happened in statistics in Lake Tahoe. Okay, it really is. And so I want to give you what it looks like, and that some people do weird stuff because they wanted to make it look like they were dropping a Siki dish, which means zero should be the top and then positive numbers below it. So this actually has a negative slope because as the years go on, the depth has gone down. Do you see that? Yeah, it's upside down, so you have to see that. So sorry about the trick question, but I warned you it's a trick question. Any questions so far? All right, so what we're interested in is a bunch of things. One is the slope. Oops, I don't want to do that. And the slope of this line, hopefully you remember, is found by rise over run. You remember doing that at one point in your life? And you could approximate that. You could say, well, from 1965 to maybe 1995, right? We went from 30 to about, looks like about 22. So the rise is -8, and the run is 30 years. Okay, so it is -8 over 30. Any questions on that? No, it's not completely linear, but it's not that bad a model either. Does that make sense? So let me explain, and this isn't math, or it's not statistics. It's statistics, but it's not the statistics of this example. And the reason why it's not completely linear is weather. If you have a big, huge year, storm-wise, in terms of snow, then lake clarity goes down. Okay, and that's because you get a big runoff. You get a lot of dirt and stuff going into the lake from that runoff, and then that's going to cause lake clarity to go down. Okay, whereas if you have a drought year, lake clarity tends to go up. So it's going to be ups and downs. There's going to be different reasons for changes in lake clarity. But what we want to do is we want to say, well, is year correlated to lake clarity? That does not mean it's the only thing that is related to it. Just means it's one of them. Does that make sense? Weather is also correlated. Okay, you can look at precipitation, and you can look at a correlation between precipitation and lake clarity, and you'll also actually see a correlation. Okay, but the difference is that we can't do much of anything about the weather. It's not that we can change the fact that years go by, but it's not that the year is causing it, right? What's the cause of this decline in lake clarity? Is the cause the fact that time went by? Between 1965 and 1995? No, the cause is us. Okay, it's all the cars we're driving, it's the pushing things, it's the pollution, it's the rerouting of creeks, it's all that kind of crap, and that stuff we can do with. Okay, so what we can say is, again, we said it was -8 over 30, which is -8 over 30. Let's do that. Let me just a minute. That one. There we go. So now if you take -8 over 30, I like to write as a decimal. It's about -0.3. I can go 1 decimal because I just eyeballed it anyway. So you shouldn't be able to go more than 1 decimal. So note that our slope is about -0.3. Actually, I can do this in Google now. Any questions on that? Okay, so I think I got to get rid of this line. I don't know if I can. So the line's going to move around. I think I need to, let's see something, just a minute. I can erase, there we go. That's better. And now I'm ready to do it in Google instead. It works better. So the slope was equal to about -0.3, approximately. I like to divide it by 1. It makes it easier to see it, and you'll see why in a bit. All right, now it comes to seeing if you remember your basic algebra. In words, what does the slope represent? Your standard couple words in algebra. When they talk about slope. Change over time, but in particular in algebra, you call it rise over run, right? Okay, that came from algebra. Hopefully you remembered that at one point in your life, because that is really important. Okay, so now what we want to do is say, what is the rise? The rise is the change in what? Change in lake clarity. So if the rise is negative, that means it goes down. So note this is, let me write this down. This is change in lake clarity, because that's the rise, over, and what is a run? What is a run? Yeah, over years. So now we can say that we're changing in lake clarity by -0.3 meters. So that's down 3 meters, or a loss of 3 meters of lake clarity. And we're changing in years by 1. So we can say that for every year, the lake clarity has tended to go down by an average of 0.3 meters. Any questions on that? Any questions? Make sense so far? Does A matter? That's the next thing to talk about. Okay, so let me remind you. Scatter plot, that was, we saw a picture of it. Regression line, I drew a line. We just interpreted the slope. Next is the y-intercept. So that's the next thing, is to get to the y-intercept. So I'm going through each of these things, and then we'll do it with data too. We'll do some calculations. Okay. Any questions on interpreting the slope? Okay. Notice the slope is always meaningful. So that interpretation makes sense. Let's go to the y-intercept. Okay, so the y-intercept. So you gotta be a little careful here. The y-intercept is not this value, which is around 35 or something, right? Because that's 1965. The y-intercept is when x is what value? Again, this is, yeah, x is 0. That's the definition of y-intercept. It means that x is 0. Let's find y. It's meaningless, but it's important. So I am going to, I think I have to draw again. Well, just so we can see it again. So something like that, right? And notice 1965, 30. I'm just going to use that as a point. Any questions on that? So now let me undraw. So note that the line goes through. (1965, 30). Any questions so far? Okay, time is not infinite, by the way. Okay. I'm not going to get into it, but there was a beginning of the universe called the Big Bang. And the end, no one knows about. So it's not infinite. It's actually finite. Okay, there is a beginning. Okay. So, but let's not do that, because you don't need no stats. You don't need that for stats. Okay. But we know the line goes through that point. Okay. We know the slope was negative 0.3. So we can say that if you remember y, and y is 30, is equal to a plus b, which is negative 0.3. So I can write minus 0.3 times 1965. Any questions on that? So that means A is equal to 30 plus 0.3 times 1965. And I can pop that right into Google Calculator. And we get 619.5. Any questions on that? Okay, so that means, and again, we're doing the eyeballing, and I'll show you how to do it better later. That means that we can say y hat. We tend to use y hat, not y, because it's just an estimate, is equal to 619.5 minus 0.3x. Any questions at all? Any questions at all on getting the equation of the regression line just by eyeballing? Okay, so now that we have that, here's a question. What is the predicted lake clarity for today? And I hope, again, this is not part of statistics class, but I hope you know what date it is, what year we're in. How do we do that? Yeah, we plug in 2020 for X. Tell me what you get. Let's see if you can do that. What do you get? I've been doing all the work. I'm gonna let you do a little work. You're not doing your head. You're always allowed to use technology. $13.5. Okay. By the way, is that okay? Would it be okay if the lake clarity was 13.5 meters? Definitely not. It would be a complete disaster. Okay. So let me tell you what happened. Okay. The good news is that President Clinton understood science and understood statistics. Okay. And he believed in scientists and he trusted scientists. It's always good to have a president that trusts science and statistics. Any guess on what happened after that day when the UC Davis researchers presented the Lake Tahoe clarity to President Clinton? Is history. Yeah, it turned out not emissions. Emissions are actually a minor piece, but all of a sudden, he put in hundreds of millions of dollars in environmental solutions in our area, in Lake Tahoe area. So huge amounts of funding went in. Fortunately, because our president understood that statistics are something you can rely on if it's done right by scientists. And given the fact that the statistics said this, the president basically got Congress to pass a bill to fund Lake Tahoe's clarity. And that's the history. It makes a big, so that's like the most important thing that ever happened in our town of positive things. I don't want to talk about the Angora fire. But the most important good thing that ever happened was because of statistics and science and our president at the time. Okay. So let me show you the picture. Notice, do you really think they stopped? Do you really think they stopped looking at it after the year 2000 or so? I think every president of the United States should be required to take and understand statistics. And science is good too. But I can be biased about statistics. So I'm a believer in statistics and understanding what to trust and what not to trust. And this is definitely one to trust. So do you think they stopped doing measurements in 2020? Now let me show you what happened. So now I can go to the real picture. And actually, I think it's that one. There we go. So now we get to see, I like, when I teach this, I like to stop in 2020 because I can show you what it used to look like and why the decision was made. And now let's look at it. Look at between stop in 2000, sorry. Look at between 2000 and now. In fact, let me copy that and pop that into our Google. And I want to just look at the 2000 and now. Okay, now they do it in feet. Feet on the right, meters on the left. That's just what UC Davis decided to do. And just a second. I know you can't see what I'm doing, but trust me, I'm doing the right thing for this. There we go. So let's look at the current graph. This is for the last 20 years or so. 19, because they don't know this year yet. What do you notice now about the regression line? Take a look. Look at what do you say about the slope of the best fit line in these points? What do you notice? Yeah, it's flat. It has slope 0. Okay, so what happened is President Clinton and staff, by the way, said, you know, if things keep happening, we're going to end up with 13.5 meters of lake clarity in 2020. I'm sure 2020 wasn't the target. That's just where we are now. But the point is, it's just going to get worse and worse and worse and worse and worse. So let's do something about it. So the first graph that I showed you was what happens if there's no work and no effort to deal with the pollution. Once they see the statistics and realize there's a problem, they put in the effort and they change the equation. And that is what statistics is all about. It's about looking at data, understanding what the data is telling you, and then making a decision based on what the data has told you so that you can make life better. And this is a case where it worked. Okay, there's still ups and downs. Do you remember why I told you why there's still ups and downs? You remember? Yeah, weather. Okay. In fact, 2011, I don't know if any of you are here in 2011, that was a big snow year. And then soon after that, we had a big drought, and notice the lake clarity got better. Remember, down is better in this case. Down is higher. And then the drought was over, and now lake clarity, you know, came back to the flat line. You see that? And that's just kind of how it is. So the weather, that's a much harder thing to do. I don't think we're going to change that one. But the pollution we can change. What will this coming winter be like? I have no idea. That you can't do with statistics. It's a long story on why, but there's too much what's called chaos. So you can't, it turns out there is no correlation between year and weather. Unfortunately, there's a warming. It's a very slow warming, and that's called global warming. So it's likely to be a degree or two higher than it has in the last 100 years. But it's only a degree or two. So that's also regression analysis. There's a very small correlation with global warming, but unfortunately, all it takes is a degree or two to cause disaster. Okay, but it's still a small correlation. Okay, on the other hand, lake clarity, there was a gigantic correlation when we weren't stopping pollution. Any questions at all on this example? Okay, I want to mention something about these guys. This first one, we have a negative slope, even though it feels positive, but it's really negative. And there's a strong correlation. Okay, these points do not all lie on a line, but I can easily visualize a line. I had no trouble drawing a line that had negative slope numbers. Negative. Is that clear? And there's a measurement. There's a measurement of correlation. And that measurement is a number. And the letter you use for it is R. So we're going to use the letter R to talk about correlation. If R is negative, then that tells you have a negatively sloped line like we did here. We had negative 0.3. If R is positive, then you have a positively sloped line. R is not the same as the slope though. R is always between -1 and 1, and the slope is not always between -1 and 1, just to let you know. Okay, if R is 0, then there is no correlation. Okay, and that is like where we have been recently. So this one's got an R equals 0. So let me write that in what I just say, but put it on paper. So the correlation R is a measure of how good a predictor the regression line is. Is for the data. Okay, you're never going. You're rarely going to be perfectly on a line. If R is 1, then it's perfectly on a line. Let me give you an example of R is 1 for data. Let's suppose I asked you, what is your height in inches? We're going to call that X. And what is your height in centimeters? Let's call that Y. Why is R1 in this case? If I took data of 100 people, and the X was your height in inches, and your Y was your height in centimeters. Yeah, just converted because there's an equation that converts inches to centimeters. Okay, and it's a linear equation. So it's perfect. It's an absolute perfect fit, inches to centimeters, right? You can go up and find that equation. In fact, just for fun, you don't remember it? Equation to convert inches. I didn't have to type the whole thing. Google knows what I'm thinking, to centimeters. And, oh, it's got to give it to you somewhere. I need a little more words on this. Equation of the line. Hopefully that will do better. Okay, 1 inch equals 2.5 centimeters, but that we need more than that. Come on, they got to have it somewhere. Okay, so it's just y equals 2.54 x. Okay, or actually it's x equals 2.454 y, so it's y equals 1 over 2.54 x. So it's an equation. You don't need to collect data. Do you see that? You know how to get inches to centimeters, but we don't know how to get lake clarity, years to lake clarity, because it doesn't work that way. Okay, we don't know what next year's lake clarity is going to be. Who knows? Okay, you could make a prediction, but you don't know. So if there is a true just equation that gets there, I'll be 1 or -1, depending on whether you have a positive or negative slope line, if it's a linear equation. But if it's data, like year and lake clarity, then no. R is something else. And previously R was like maybe 0.8, negative 0.8, but now it's more like close to 0. Do you see that? Any questions on that? So far, so good? Okay, so now let's do, so that's what R does. And the last thing to do is R squared. And this seems like it's kind of even silly to talk about. I hope you all know, if you know what R is, you know how to find R squared. If you have a calculator or a computer. I hope you know how to do it. You take R and you multiply by R, and you get R squared. So one of the things that you notice is that if you understand a little tiny math, is that R squared is always positive, right? You can't have a negative R squared. You square a number, you get a positive. You can get 0, but you can't get a negative number. So it's always non-negative. So R squared is the following. So this tells us the percent decrease in, not percent variability. So like standard deviation. In the y variable, when you know the x variable. Okay, it's very abstract. But let me give you an idea that you can probably visualize pretty well. Imagine we were in good times and we actually had elementary schools where kids went to school. But you could probably imagine that. You might have to close your eyes to imagine it because it's been a long time. But you can imagine that could happen, right? And you looked at just the height of kids in the school. Is there a lot of variability from kid to kid at an elementary school in terms of height? Okay, think about a kindergartner and a fifth grader. Yeah, there's a lot of variability. They're all over the place in terms of height. If you didn't think so, you haven't been to a school in a long time. They're all over the place, right? Okay, but if instead you walked into a third grade class where all the kids are similar age, there's still variability, right? But is it the same or is it less variability? Yeah, it's less variability. Okay, and it might be, say, 70% less variability. Okay, again, don't quote me on the number 70%. But let's say it's 70% less variability on average by if you looked at a certain grade instead of looked at the whole school. Then what you would say is that R squared for measuring year or age versus height is about 0.7. Because knowing the age will decrease the variability in height by around 70%. Can you picture that? Okay. On the other hand, if instead you did the same thing, but not in elementary school, let's say you did it at a college, what do you think R squared is going to be? And you looked at age versus height. How do you find R? We'll get there, I promise. Remember, we have more time today and we have 2 hours on Thursday. I'll give you an example. Thursday, you can do a lot of work on as groups, hopefully. Hopefully you'll all come. So what do you think about a college? What do you think R squared will be up for the college? If it's age versus height. Okay, so if the x variable is how old you are, and the y variable is how many inches you are. So we have two variables, and you can collect the data, plot the points, just like we did with the year versus depth of clarity. You could do age versus height. What do you think R² will be when you do that at the college instead of in elementary school? The hint is it's very different. Age doesn't matter, so what do you think the R² will be? So how much decrease in variability is going to be if you only look at people of the same age in college? Don't you have to think about the elementary? The key is age doesn't matter. So by knowing what age they are, how much decrease in variability will there be if it doesn't matter? Zero, exactly. Exactly. So if knowing the age has nothing to do with the height, the person's height, then you're going to have an R² of 0. Do you see that? On the other hand, if knowing the age has a lot to do with knowing the height, then you're going to have a much higher R², like 0.7 or 0.8. Okay? It's not going to be 1 because knowing the age is not an absolute determination of the height, but it certainly helps in the elementary school. Any questions on that idea? All right, so now what I'm going to do is let's go ahead and find it. Okay. What I'm not going to do in this class is I'm not going to show you how the mathematics works. What I'm going to do is show you how to use a calculator. Okay, and we'll do the one I created. Should be in here. Oh, well, there it is. Okay, first thing, because it's going to be important for quiz, for example, is which calculator number do you think we're on now? Yep, 23. Okay, so this one's gonna be a little bit different in terms of how you enter data and stuff. There's more that we don't know yet, but that's okay. So let's just do us, even though it's gonna be a very small data set. But let's do it. Is there anything you're interested in? There's two variables that might have a correlation that we could ask each other. If not, I'll make something up. I don't see y'all jumping in. Okay, how about, and by the way, I'm not going to say who did what. Chat box is not on YouTube, so no one will know what your answer was, like who did what. And I'll even put mine in there too, and I'm not going to say what I did. I'm not going to say it out loud. All right, how about, how old were you when you experienced your first passionate kiss? Is the first one. Does that make sense? And how old were you when you took your first college class? And we'll see if there's any correlation. So you have to give me two numbers. The first is age of passionate kiss. And the second is age of college class. And I'm going to let you do one too, because I need more data values. So I'm going to put 16 and 16. That was somebody's, it could have been mine. I'm going to hit plot point. And there we go. Then I'm going to hit 12 and 18. And plot point. Okay, notice what it's doing right now. Not very interesting because there is a line that goes through those 2 points. There always is for 2 points, as long as they're different points. Then we have 13, 18. Plot point. And then we're going to have 13, 17. And I'm going to plot point. Okay, this is a very small data set. And anyone else? I know who you are. No, I can't force you. All right, so the first thing is we have this small data set. Unlike, by the way, the UC Davis thing, this is not trying to trick you into some kind of slope thing. Is the slope positive or negative? Just by looking? What do you think? Yeah, slope is negative because notice when you go from left to right, it goes down. Okay, that's how we know it's negative. Does it look like there's a correlation or does it look like it's all over the place? Pretty scattered, but I'm noticing that I'm definitely seeing that as you go right, you're going down. It's not that scattered. Okay, I could visualize this line. I would not draw a line going up, would you? If I didn't see this line, I would know it goes down. So let's take a look. All right. R squared is 0.82 about. Okay, now again, we only have a data set of 4, so you shouldn't be doing this, by the way. But when you have a small data set, you do what you can do. So what we can say is that there is a variation. There's pretty much variation in age at which people took their first college class. But if you're told how old they were when they had their first passionate kiss, then that variation on average declines by about 82%. Does that make sense? Okay, here's the equation of the regression line. Y equals 24 plus negative 0.5x. And in particular, the slope is negative 1/2. So what we can say is that on average, for every year that somebody waits to have their first passionate kiss. Oh, is that plus or minus? That's just because it's not in pretty point. This is plus negative. You could make it a minus. So it's often A plus BX is the idea, and B is negative. Does that make sense? So it's not plus or minus, it's a plus a negative value. Yeah, it can be simplified if you want to. So what we can say is that for every year that somebody waits to have their first passionate kiss, on average, they go to college a half year sooner. Okay. Now again, this is a very small data set. I would not tell this all about society. Okay, but if you had a large data set, then this is something you could do. And if this were the true regression equation, then that tells you something. You know, that if you were thinking about counseling in middle school, for example, and you didn't want people to have to wait very long to go to college, you know, get a delay, then you might get these kids not to be so promiscuous, at least kissing promiscuous. You see that? If you cared about not having to delay for college. Okay, what about the y-intercept? Is it meaningful? What do you think? First, can 24 be the year at which someone starts college? What do you think? Yeah, so the y value sounds okay. On the other hand, what is the x value for the y-intercept? Always, for any y-intercept. 0. Can you have your first passionate kiss when you're 0 years old? Definitely not. Okay? When you're 0 years old, you're not thinking about passion. Okay? You're thinking about milk. You're not thinking about passion. Thinking about milk and mommy and daddy, and that's about it. You can't even say mommy and daddy, but you're thinking about them, hopefully. Again, we don't know exactly, but we know you're not thinking about passionate kisses. Okay? If someone else had a passionate kiss on them, that person needs to go to jail, by the way. So this actually also doesn't have any meaning. So you only have meaning if both x equals 0 and the y value of the y-intercept both have meaning. And the value of x has to be at least not too far from the data set. So in our first example, it didn't really have meaning either. Any questions on this? Any questions? Okay. So again, we have all our different things. Here's what we're not doing today. The last line. There is going to be a hypothesis test, but I'm saving that for next time, for Thursday. We have a lot more. We're going to do lots of examples on Thursday. We're going to do a little bit today, but I want you to know how to understand the y-intercept, if it's meaningful, how to understand the slope, which will always be meaningful, to understand the correlation, r squared, to know that r and the slope always have the same sign. Okay, those are really important things. Any questions on any of this so far? Okay, now I'm going to put you to work in a weird way. So I can go back. Actually, it's right here. I'm going to give you 5 minutes to do a game. The game I made. So let me put a link in the chat box. Okay, and what I found is that this helps a little bit understanding correlation. And it's fun. I'm not very good at it, by the way. Unlike millennials, I'm not a big gamer. But if you're a gamer, you're good at this. Okay? But you have to know math too. You have to understand correlation. Okay, so here's the rules. You'll be given a correlation, and your money will be flying through the air. You must keep shooting down your money until the correlation for that scatter plot is within 0.1 of the correlation goal that is shown. You can destroy your money by shooting it down. But when you do, you're going to lose that much money. And the bill will turn into a point that becomes part of the scatter plot. You start with $100. Try to end up with as much money as you can. Click the start to start the game. Use the buttons below or left or right arrow keys to rotate your gun and the up key to shoot. Got it? So I'm going to hit start. And notice our goal here, which is different for you guys, by the way, is negative 0.8 for the correlation. So I am going to move my arrow a bit. I'm going to shoot. And I need to shoot some more. Okay, notice my R is -1. I just lost $2. And let's shoot some more. That missed. Like I said, I'm not very good at this. I'm good at programming it though. Oh, that's not what I wanted. All right. Uh-oh. My correlation just went way close to 0. Oh, correlation is 0 now, but that'll change eventually. Getting there. That one mistake cost me badly. All right. This is tough because of that one mistake. I'm not going to necessarily win right away. The strategy is trying to end up with dots that have the perfect correlation. Do you see? So right now, because of this one over here, I really messed up. So what I want you to do is I want you to go to this link in a couple minutes. Trying to make a line if your correlation is close to 1 or -1. If it's close to 0, you better not make a line. Yeah, you could do all these Donkey Kong, Pac-Man. By the way, I've programmed all these with math too. Not Donkey Kong, but I've done Pac-Man and Frogger. Unfortunately, I did it in Java, and it doesn't work on most browsers anymore. Such a bummer. But I made Logger instead of Frogger, which is Frogger for logarithms, and Order of Operations Pac-Man. So I made all those different games. That was a sabbatical I did. All right, so let's see if you can go to that link, and I'm going to give you a couple minutes. I'm going to be quiet now. Give you a few minutes to see if you can win. Give it a shot. So you should all be, you don't have to close Zoom. You just have to make sure that you're on a screen where you can go online and play. Should work on a smartphone too. But I would have no chance on my smartphone because I'm terrible with my smartphone. So give it a shot. Give you a couple minutes. And if you have questions, I'll be here. I'm not running away or anything. We'll drink a little water. Ha, I finally won. Give you one more minute. I think you get 20 bucks if you win. I think that's how I programmed it, if I remember right. Okay, what do you think? Do you think you have a good feel for what R is? Or are you just playing? So the hope is that, you know, if you play this enough, you'll really get the idea. Oh, you did better than I did. I'm terrible at these kind of games. But as you can see, I know how to program them. Okay, and nothing like this has never been programmed before. So that was the first. So I don't know if other people will use it. Okay, so you don't know what R is. So take a look at this example. Notice that as X increases, Y also increases. You see that? So the slope of the regression line in this example, the one I'm looking at now, is positive. You see that? It's not quite slope. So let me do some other examples and we'll see. Okay, so let's hit start again. Okay, I gotta hit a bunch. Two's not enough. Two's never interesting. Okay, so my slope is -1. We just have a -1 slope line, but again, 2 points is never interesting with regression analysis. Okay, so now we got 3 points, and now the slope is -0.16. Now you notice the line is not a great fit. There's no great fit for these points. It's hard to kind of even imagine a line going through them. And I could do more like that. I'm trying to do one that has not a great fit. I think I missed. Yeah. You guys would probably do better than I am in explaining because I can't even hit the things. Sorry. I almost hit one. There we go. Okay, so now we have R as 0.52. You can kind of maybe see a positively sloped line. Do you see that? But not so much. Does that make sense? Okay, now we have 0.51. Not a great correlation, not a very high correlation, not close to 1. Not missed. Just not very good at this. Okay. So again, now it's kind of all over the place. Do you see that? Yeah, it's how accurate the best fit is. So for example, what do you think R is? So tonight, at say 10 o'clock tonight before the moon comes up and after the sun's way down, and you look up in the sky and what do you see? And in Tahoe, we can see it well. In LA, forget it. You can see stars, right? What do you think R is for the stars? Yeah, R is going to be very close to 0 because there isn't some linear fit for the stars. Does that make sense? R could be 0 in some different ways. One is if the points are all over the place. The other is if the lines are horizontal. If the points are on a line but it's horizontal, that will also give you an R equals 0. but most of the time it's all over the place. Whereas if the lines have a nice fit of the line, then and the slope is positive, R will be close to 1. If it has a poor fit, if it has a nice fit to the line and the slope is negative, R will be close to -1. Does that help? And if you play this game and watch the R as it goes, then it'll make sense. It's in some pre-calculus classes. It's not in the high school pre-calc. Did you have it in high school? Yeah, I didn't think so. Yeah, the high school classes don't teach it in pre-calc. Or they didn't, and now they're starting to. It's kind of weird. It's in Common Core pre-calc. It wasn't in pre-Common Core pre-calc. So the pre-calc is even a hard one to talk about. It depends on how old you are. Okay, if you are 16 right now and in pre-calc, then you're getting R. So it's part of the new Common Core standards. Okay, if your teacher is teaching Common Core. Okay, and not just pre-calc, but actually intermediate algebra too. They do R. They do. Any questions at all about this example? Okay, I want to have you guys do another one. We still have a little more time. Not this again, but let's see if you could come up in the next 5 minutes with, I don't think there's enough of you to do breakout rooms, unfortunately, but let's see if you can come up on your own and you can collect data online with 2 variables that are quantitative and come up with the equation of the regression line and come up with the correlation and R squared. Maybe you can even interpret it like I've been doing for the last couple hours. And in case you don't have it, in the chat box, I'll put my calculator that I made. Don't get a huge data set because it'll take all day and we don't have more than 10 minutes. But let's see if you can come up with something. Like I said, there's a lot of things you can do. So for example, it could be prices of different things that are related, in different areas or something like that. It could be weather related. It could be, there's lots of things, but it has to be 2 things that might be related to each other. And you're not gonna be able to do a survey. You're gonna have to go finding data. It could be date and something else. It could be, I don't know, something like how far a town is and how much it costs to fly if you want to get to that city. There's a lot of things you can do regression analysis on. The thought is maybe if farther, you probably have to pay more. Maybe true, maybe not. Pretend we're actually allowed to travel. So there's a lot of things you can go and look up. It could be baseball. Okay, not this year because there's no baseball going on. Could have been last year's baseball. It could have been, I don't know, batting average and home runs hit in the year. There's a lot of things you can relate and see if they're related. So I'll give you about 5 minutes to do that. Come up with some data, pop it into the calculator, maybe 5 or so points. Don't get too many because it'll take too long. And let's see what you can do. And I'm here to help if you have any questions. And so is Anna. Okay, let's continue on. And I'm gonna let, Erez, you said you at least got your equation, hopefully. Can you explain what you did?
Yeah, so I did consumption of bananas per capita
Mhm.
per year.
Mhm.
And I just like pulled a few years and plugged those points in.
But what were the two, what was X and what was Y, in other words?
Oh, X was years and Y was consumption of bananas per capita per pound.
Okay, so it was year by consumption of bananas. Okay,
Yeah.
maybe there's a
Pounds-
relationship. And
pounds-
what'd you get for your equation?
I got, hold on. I got Y equals negative 1,537.69 plus 0.77x.
Okay,
And
and how do you interpret the slope?
so I said for every year, consumption of bananas per capita grows by 0.78 pounds on average.
Okay,
And then I just got to
which
my,
is not, if we're talking about per year. I think I ate that much just today.
yeah,
I had a banana.
right. But that's just how much it grows per year. But
Right, so you can see it's only a little tiny bit. What about the y-intercept?
the y-intercept,
Mhm.
I haven't interpreted that yet.
Okay, what do you think? Do you think it has meaning? What was the number?
Negative 1,537.
So does the y-intercept have meaning?
I don't think so,
How come?
because you can't eat negative pounds.
Exactly. You can't have negative pounds of bananas, so the y-intercept definitely has no meaning. Is that clear?
Yeah. But
Yeah,
what if,
so it's not interpretable.
so if it was
Okay.
positive, would it be, I mean, what if it was positive, but just really low, like, and just inaccurate?
Well, the thing is, if it was positive, the first thing you would have to say is, when you looked at your data, did you do things from a couple thousand years ago? Or were all the data like the last 5 years or 10 years or something?
Right. Because if you just do something from current, then it can send it way down for a few thousand years ago, right?
If you only do things from current, then you shouldn't even be looking and trying to interpret what happened in the year zero. Does that
Right.
make sense? On the other hand, if say you did the year 500 BC and the year 200 AD, you're maybe 1200 AD and today.
Yeah.
Let's say that was your data. Then it makes sense. Do you see that?
And then for my R, I got 0.9.
Okay.
I'm not sure.
And 0.9, interesting.
Yeah.
Okay.
So close to a good fit.
Yeah, that's a very good fit, by the way, or decent fit. What about R squared?
0.81.
Good. Funny thing, same as mine, right? Remember that?
Right.
0.82.
So how would I interpret those last two?
Yeah, how do you interpret? So the first thing is R is 0.9, so there's a positive correlation. Do you see that?
Yeah, because the slope, it slopes upward.
Yep, and it's pretty strong positive correlation.
Yeah.
Because it's close to 1.
Right.
And now the 0.81.
But
says
how,
that, huh? What's that?
what would is there like a wording that you're looking for interpretation?
Yeah, so for the 0.81, you would say that there's a pretty large variation in per capita banana consumption.
And what about R?
But well, let me keep going. But if you just focus on a small time period, like maybe this year and last year, then that variation is decreased by an average of about 81%.
And that's per year?
No, that's when you look at a small time period.
Oh, okay.
So in other words, if you don't look at the last 200 years, but you just look at the last couple of years,
Yeah.
the last 5 years, you see that? So if you focus on specific years that are real close to each other, then the variation is going to be decreased on an average of 81%.
Okay.
Does that make sense?
Mm-hmm. And then for R?
What's that?
And then is there a wording for R or?
Yeah, R is just there's a strong positive correlation between year and per capita banana consumption.
Okay.
That's as much as you can get there. So R is a bit easier. R squared is hard because R squared is a new thing for y'all. Very new, right? R isn't too bad because you've kind of heard about large correlation.
Yeah.
In your life, probably, right? You've heard those words. Okay, R squared is much harder.
I see. All right.
All right, Michelle, did you get a good equation?
No.
You could chat box or talk, one or the other.
No, I didn't. I did it completely wrong, and I couldn't get the data that I had acquired to enter into the calculator.
Oh, really? Did you use that link that I gave you?
Yeah, but
So you just
somehow I could only get things to enter into the into one part. I couldn't enter it in the data bar.
okay. Let me share my screen then.
But I think I might have understood it improperly and not gathered the right kind of data.
Okay, so what was your first point? What was your first X and Y? It should be numbers.
40 and 52.
Okay, so all you do is right here, you put 40. And right here, let me actually, let's go new plot because we need to start over. So 40. And right here, you put 52.
Uh-huh.
And you hit plot point.
So I think
That's
that's
it.
where I made a mistake because I was trying to enter it all in the data bar. I was able to enter 40 and 52 right where you did, but I didn't click on plot point. I was trying to enter all of it like in the other calculators separated by a comma. I tried the parentheses, stuff like that. So I didn't enter it properly, but I can give you the rest of the numbers now.
Yeah, hopefully not too many because we kind of.
No, it's only 4 because we only had a few moments.
Okay.
Next is 97 and 40.
And you hit plot point.
93 and 19.
It's always easier to watch than to do, isn't it?
Yes.
And the next one?
89 and 40. And that's the last one.
Yeah. And again, we didn't have much time. So, in the real world, you do a couple hundred of them typically if you can.
Yeah, it took a moment to be creative and think of something to pick. The bananas was good.
Yeah. And what were the variables here?
I'm not sure.
What did yours correspond to, I mean?
I didn't get any further than that because
No. What was your, no. I'm saying is what,
Numbers.
what, 89 what's? Were they bananas?
$89.
Dollars and 40 what's?
Rides.
40 what?
Rides.
Rides.
I was
Okay, so then you can go and you can look at the equations of regression line. Okay, so for every dollar increase, rides tend to go down on average by approximately 0.3. And we can say that if it's free, that's $0, right?
right.
Then you would expect to have about 66 rides.
Seems a lot better than the real prices.
What's that?
A lot better than the real prices.
And remember, you only have 4 data values.
Right.
And then you have your R is negative 0.69 about. Your R squared is 0.47. Okay. So again, small data sets, you gotta, never trust anything with small data sets. This is just an exercise, this is not something to go by like, oh, that 4 is good, never ever do sample size of 4. Michael, does that make sense how you put it in now? Yeah, so you just put it in and hit plot point. If you're told what to do, it's really easy. If you're not, then it might be hard. And I think, did I have instructions here? I don't think maybe I need to put some better instructions here. Any questions on any of this?
Yeah. Can you interpret the R squared?
In this case, okay. So what we could say is that there's a if you just look in general, the number of rides, there's a pretty big variation of the number of rides, right? Okay. If you just look at the data values and just ignore the prices, then we have a pretty big variation. You can see, in fact, it goes from 18 to over 40. That's a big variation. Do you see that? On the other hand, if you just focus on dollar amounts that are all kind of close to each other. So if you keep your dollar value, you keep your price constant, then that variation in number of rides that you expect will go down by about 47%. Okay, so it doesn't mean that you have a complete deterministic. If you know the price, you know how many rides. But you can say is that there is a drop in the variation if you know the price. So there's going to be other factors also that contribute to maybe 57% of this variation. And that might be weather or whatever it might be, you know, day of the week or something like that. Does that make sense?
Sort of. I need some practice on that though.
Yeah, this is the hardest part of the whole chapter.
Okay.
And you'll get to practice once on the quiz on Thursday, and then we'll practice more on Thursday. Just that's what we're going to be doing. Okay, so Thursday is about practice. Does that make sense? Okay, well, we're officially at 3:30. Believe it or not, I've been on Zoom since 8:30 with no break.
Man.
Except your quiz. Yeah. And I'm Zooming tonight too for that next class. But I'm going to stop recording.